Okay. All right, so we're going to continue talking about Gauss's law. We talked a lot about spherical geometry last time. So we talked about point charges, uniformly charged spheres, hollow spheres. Towards the end, we talked about a line charge. The one thing we did not talk about was infinite sheets, which is what we're going to talk about some today. Um, so if you remember in one of the worksheets that we did, I just sort of casually told you that, oh, by the way, when you have a big sheet, so a big metal sheet that's all charged up, you get a pretty close to uniform electric field from it that's according to this equation. I didn't really say exactly where this came from, but today I'm gonna show you where it actually comes from. And there's a fly in my office in my house. All right. So it's the charge divided by the total area of the metal sheet. Interestingly, it does not depend on the distance. Now, in the next slide, there's a video that I'd like you to watch. I'm actually not going to play it in the middle of this video because I'm having some sound issues. I think it will sound better if you click on the link and watch it yourself. Also, if I include it in the YouTube, when I post this to YouTube, YouTube could take it down because of a copyright issue. So please go ahead and watch the video. Broadly speaking, the video will show you that Walter Lewin is going to take sort of a charged object on a string, and he's going to put it up close to an actual thing that's hooked up and all charged up. And he'll show that, as you move it, a couple of inches to maybe a foot or two, that angle doesn't really change. The angle that the charged particle is hanging from, the charged thing is hanging from, I guess it'd be hanging this way. That angle, as he moves it closer and further away, is not really changing by much. And the reason it's not changing by much is because it turns out that the electric field very close to this object is close to constant. The thing I like about the video is that he points out that if you take this apparatus, far enough away from the thing, that eventually the electric field does start to drop off, more or less like a point charge. So this equation only applies if you're overall pretty close to this thing. But that's the thing I like about the video, and that's something I hope that you can pick up as he's talking. So I'm going to skip through it now. There we go. So I think I just said the things that I like about this video because it helps to kind of justify that. Now I'm telling you that outside of a sheet of charge like this, that the electric field is uniform. You can also put another sheet here. By the way, a fun question is, which one of these is the positive sheet and which one of these is the negative sheet? So it's a fun thing to sort of puzzle over here. The answer is that electric fields, so these arrows are the electric field. The arrows always point away from positive charges and go to negative charges. And so therefore this end has to be the positive end, this end has to be the negative end. And so in this course, I will casually say, oh yeah, the electric field between two charged plates, one positive, one negative, is constant or uniform. This is an actual simulation of what that looks like. And so you can see that the length of these arrows is pretty close to uniform, right? And the colors on this plot also indicate the field strength. And you can see it's almost exactly the same color in the middle of this thing here. Now in the ends, it's it's not perfectly constant, right? The field starts to go in different directions. It's stronger over here than it is in the middle. But to a great extent, the field is roughly constant in the middle of these things. So before I just sort of go on and assume that this is obvious, I just wanted to point out, like, yes, this does break down, but it breaks down like over here, right? So if you're trying to create a uniform electric field for some purpose, this is a pretty good way to do it, as long as you're sort of staying in, here somewhere, right? That should work great. Now, we've not yet applied Gauss's law to infinite planes. Generally the point of doing it is that if you're trying to calculate this electric field, technically you would have to like sum up all the little charges here that contributes to the electric field, say in the middle of this thing, and then all of the charges over here. It would be even more painful than that one calculation where we had the hollow sphere and we're calculating the repulsion and traction and stuff like that. So But Gauss's law, once again, gives us a nice shortcut. And I'm gonna show you how to do the shortcut, I think in pretty soon, and maybe the next slide. All right. So I would say the best shape for doing this, because whenever you're doing Gauss's law, you have to use some sort of Gaussian surface. The Gaussian surface is always an imaginary surface. So if you're in a problem and you're trying to think of this object as a Gaussian surface, you're probably thinking about it in the wrong way. So Gaussian surfaces are from imagination land, is where they're from. And so this is a Gaussian surface that works particularly well. Again, you can use whatever Gaussian surface you want, but some of them are easier to work with than others for various purposes. So there's our Gaussian surface, and we're going to put it so that it's sort of like, it's kind of bisecting this sheet of charge. So it's going all the way through. You can kind of see the dashes on the other side. And that's what we're going to analyze. Now, if you remember with the cylindrical geometry, we talked about how there's a flux through this end of it, there's a flux through the far end of it, and then also potentially a flux through the middle. And so we're going to do the same sort of thing here. So this crazy-looking integral ultimately breaks down to these three surfaces. And I'll give you a hint, which is one of the surfaces is going to turn out to be 0. But why is the question. So let's think about this. So we got this surface. The next thing to really think about is sort of what are the area vectors here, right? So on this thing here, this contribution, this thing here, the area vector is like this. We kind of know the electric field is going to be pointing away from it. I mean, we don't know what the strength of it is, but we do know it's pointing away. And so there's a dot product here. Dot products involve the cosine theta, where theta is the angle between these two vectors. Well, the angle between these two vectors is 0, right? Because they're pointing in the same direction. So you've got so you got something like this. You've got a cosine theta. Part of why you can go from here to here is that you expect that the electric field will have basically the same magnitude going from this side of it to go, anywhere along this circle here. The electric field should have the same strength. There's no real reason to believe it's going to be significantly larger and sort of in this part of the circle than the other part of the circle, right? Especially if we're not moving any further away from the sheet. So that's part of why you can take the electric field out of the integral, and then you integrate with the area. That gives you the total area. With the dot product there, that gives you the cosine. Cosine of 0 is 1. And so the electric flux through this part of the Gaussian surface is the electric field there times the area of that surface. Again, the area of our imaginary Gaussian cylinder. All right, so this part is definitely not 0. Okay. Let's think about the next part. The next part, let's talk about this other face. Now, whenever you have an enclosed object, again, the area vector always points perpendicularly away from it, but it also points away from the center typically, right? So over here, we had the area vector pointing this way, which is away from the center of the object. Over here, it's on the other side of it, so the area vector is perpendicular, but instead of being this way, it's pointing away from the center. Now, because it's on the other side of the charged sheet, that means that it's over here where the electric field's going the opposite direction. So in spite of the fact that we're all the way on this other side, and the area vector is going this way, well, the electric field is also going this way. And so the angle between those two is also going to be 0. Cosine of 0 is 1. And so you get the same amount of flux out of going through this surface as you do from this first surface that we considered. So this thing is also going to be that electric field times the area. Again, everything on that surface is the same distance away from the sheet, so that's not crazy to think about. Now this last one, and I already gave you a hint that one of these is going to be 0, but this last one, here's the area vectors, right? So this is the thing in the middle, right? The area vectors are pointing perpendicularly away from that. But we know that the electric field is sort of like doing this, right? And so even though the electric field, we don't know too much about the electric field, but we do know it's doing this. And so that the angle between these two things is going to be close to 90 degrees. I mean, you can calculate what the area of this inner thing is 2 pi L, 2 pi r times L, things like that. But the angle between those two things is going to be pretty close to 90. And cosine of 90, if you put it in a calculator, gives you 0. And so in fact, you get no flux out of this thing. So there you go. So you end up, so this crazy looking integral at the end of the day ends up being, you know, E times A, but twice that, because there's the front surface and the back surface. So you end up with the electric flux ends up being this. Now the last part is the charge enclosed. And sometimes the charge enclosed is the easiest part. Sometimes the charge enclosed is the hardest part. But the question is, how much charge is actually inside of our little cylinder? Part of the answer is that, well, it depends on how big the cylinder is, right? Because the cylinder is from imagination land. It's not a real cylinder that someone constructed. So it's going to depend on what the dimensions of that thing is. But if you figure that there is a certain amount of charge per unit area on this sheet, then the amount of charge that's inside of our cylinder is going to be that charge per unit area times the area of our cylinder. And so again, so the charge per unit area, it's a Greek symbol called sigma. That's going to be constant. And so that means that the charge enclosed inside of our Gaussian cylinder is going to be this times A. I mean, this is really sort of Q total divided by A total. You know, the total charge of the total area on this sheet, if it was a real like metal sheet that we're working with. But in any case, you get something like this. And what's interesting is that it depends on the area of the Gaussian surface, right? So the bigger the Gaussian surface, the more charge it enclosed. But here's the thing: is that the bigger the surface, you know, the bigger this area, the more electric flux is going through our Gaussian surface, and so that gets bigger too. And the two things sort of cancel each other out, right? We're saying, you know, half as small, half as much flux. Those things cancel each other out, and it allows us to solve for E, which gives us, you know, you divide both sides by 2, you get sigma equals twice epsilon naught, where sigma is, you know, the total charge over the total area. There you go. So that's ultimately where this equation came from on the worksheet from a day or two ago. Now there's some conductors things that we can talk about, which sort of relates to this. In some ways it relates to what we just did, and in another way it's sort of a new idea of sort of talking about what electrons are really doing when they're inside of a conductor. So in any case, this is from one sheet, right? But if you put two sheets together, and then you put another piece of metal in between them, the question is, what is the electric field in the middle of the sheet? So again, this is a piece of metal in between. So this is a charged up piece of metal here. This is a charged up piece of metal here. If this piece of metal was not in the middle of it, you would just have an electric field going from this side to this side, right? Because the force on positive charges would be to repel away from this thing and to be attracted to that thing. So there'd be a nice electric field going from this way to this way. But what happens when you put a piece of metal in there? And that's what we're going to talk about. I talked a little bit about this in class over Zoom, so I want to make sure I get a nice recording of it too. But if this piece of metal wasn't here, you would get an electric field that sort of looks like this, right? But what's interesting is that because in a metal, in a conducting metal, there are free electrons, the question is, what direction is the force on an electron that's inside of this piece of metal? It's very tempting to assume that the force on the electron is this way because there's these friendly arrows pointing it this way, right? But these arrows are electric field arrows. The electric field is always the direction of the force on a positive charge, which means that the electric field always points in the opposite direction of the force on negative charge. So if you had a negative charge here, the force on that thing is going to be this way, like that. And so these electrons are going to get shoved this way to the left. And in the end, those electrons are going to leave behind positive charges on this end, right? Because there's sort of charges missing over here that used to be there. And those electrons are going to move until which point there is no electric field inside of this thing. And the reason is that because if there was an electric field inside of this thing, well, the electrons can move, they would continue to move. And so the electrons continue to shift around until the electric field is zero. If you don't believe me, there's a nice interactive here that I can run. I did not make this, but I have lots of respect for the people that did. They did a very nice job on this simulation. It's a little, I mean, they have the ions here vibrating because they're, things that have a temperature are vibrating, and everything is sort of wiggling on some level. I'm going to go ahead and click low temp just because I'm not so interested in that behavior right now. But you have lots of electrons, and they're sort of bouncing around, and it's actually giving us a count of how many electrons are on this side and how many electrons are on this side. So as a context to this, maybe you believe me that a neutral piece of metal, when put between these two charged plates, maybe you believe me that, okay, in the middle of that thing, the electric field is going to be zero. Like, maybe that's not so crazy to agree with, right? But what if this thing has an overall negative charge, or this thing has an overall positive charge? Is the electric field in it still zero? Is kind of what is one of the things that this simulation can help us talk about. Because when I click this button, it's going to add electrons to this thing, and you'll actually see the number of electrons skyrocket on this side, and then it's still giving us the count of electrons on that side as well. It's also going to show us the electric fields going on as all of these electrons move in response to it. So let's go ahead and do that. You guys can feel free to try this at home. It should work on iPads or wherever. So I'm going to add electrons here. Here we go. So adding electrons. See how many electrons were all of a sudden jump on this side? So I'm adding electrons here. Our metal is overall negatively charged now because I've added electrons to it. And a lot happened there. So let me try this again. So we're going to add electrons to it, right? You can see the electric field here is pointing this way, right? Because the electric field always points towards negative charges. We have an excess of negative charge here. And so there was electric field inside of this metal. And because there's electric field inside of this metal pointing this way, the force on the electrons is actually that way. And so what happens when you put a whole bunch of negative charges on this thing, those electrons all fly away and go over this way until eventually you have an equal number of electrons on this side and an equal number of electrons on this side, and you end up with no electric field inside of it. Why is there no electric field? It's because if there was an electric field, one of these electrons would move in response to it, and once it's moved, it's going to change that electric field because it's going to affect that electric field until it disappears. And so one of the interesting debates that we had in the Right Pat group, so I do a lot of laser research, I'm going to tell stories about them all throughout the semester, is that we would have these debates as to, so we would shoot a laser pulse at this column of water, this tiny little column of water, and it would accelerate electrons out of that, or protons, or do something else. And so we would have debates as to how quickly this electric field equals zero process can happen. We would have these models for what's going on that would assume the electric field is quickly goes to zero, even in the midst of this super crazy, intense laser pulse. And I was of the mind that everything was happening much too quick for any of that to happen. But my students would run simulations of all this, and lo and behold, the electric field is pretty approximately equal to zero inside of the plasma when all this was happening. And they sort of had to, run the simulation showing it was happening, and I had to say, okay, you got I've changed my mind about it. And those laser pulses are, less than 100 femtoseconds in duration. And so the moral of the story that I'm trying to get at here is that Electrons have an incredibly tiny mass, 9 times 10 to the minus 31 kilograms, which allows them to move very quickly in response to these fields. So when I say that the electric field inside a conductor is 0, what I'm really saying is that the electrons move in response to whatever electric field gets produced. Just almost instantaneously, they can make these kinds of movements. It's quite remarkable how fast that they can move. So again, when I say the electric field is equal to 0, you and I both know that there's this split-second moment where it's not 0. But the point is that that moment is just incredibly short, like faster than the fastest oscilloscopes can really pick up. Okay, so again, we've decided now that for a neutral piece of metal in between these two plates, the electric field is 0. Even if this metal was charged up, positively or negatively, inside of it the electric field is going to be 0. There might be different charges build up on the edges of the thing, but inside of it the electric field would be 0, because if it wasn't 0, the electrons would move until it was. Okay. All right. Now, what are insulators? So insulators. We talked about insulators a couple lectures back. What happens if you put an insulator in here? Well, if there wasn't an insulator here, there'd be something like this. An insulator, the electrons are not 100% free to move inside of an insulator. And so because they're not free to move, you're going to end up with, it's not going to be able to totally zero out the electric field inside of this thing. And so we're going to come back to that later in the course when we talk about capacitors. But because electrons can't move as freely in an insulator, the electric field is not going to be as close to 0. All right. Other applications of this stuff. So I really like this demo. Unfortunately, it's not clear to me that you guys can see it on your computers, but I can show it to you on mine because it's built in Flash. This is a nice demo, and it has sort of a uniform sphere in the middle, surrounded by a sphere that is either a hollow sphere that is either an insulator or a conductor, and you can decide whichever one that you want it to be. By insulator, what that really means is that it is sort of like a plastic sphere that has charge uniformly distributed over it. So if I wanted to put charge on the shell here, for example, if I wanted to slide this up, you can kind of see how all of a sudden you get these electric field arrows there. So I can charge that up, and then I can make this thing an insulator or conductor. Actually, I guess the insulator conductor thing is actually the thing in the middle. Sorry about that. So it's either it is a plastic thing in the middle, uniformly charged, with charge in it, or it's a conductor. It's some piece of metal that may or may not be charged up. So what you can do is you can kind of change these values around, and then you can go ahead and plot the result. You can click plot, and you can kind of see what happens. So for me, this was actually the inspiration for the worksheet that I made. And so you can kind of see what's going on there. Okay, so I think that the idea of this thing is the outer one is definitely metal, right? It doesn't even give me an option to change the outer one metal. How do I know that? Well, as this thing was scanning through the radii, I noticed the electric field is 0 when we went from B to C, which is sort of from here to here. So that tells me that this outer hollow shell sphere thing is some kind of piece of metal. And then because this inner sphere I had selected as a conductor, you notice that the electric field here kept it 0 until which point we got sort of just outside of it. And then we could sense the electric field there. In a minute I'll change this to insulator. But the point remains that this is a sphere that is charged up with -2 charge. And so in spite of the fact that this thing is charged up, inside of it the electric field is 0. And I can change the charges if I wanted to. I'm going to go ahead and change it in the inside from conductor to insulator, which changes the color of it. It doesn't change a whole lot more. But then I can plot it up again. And now it's not true that the electric field inside of this thing is 0. The electric field continues to climb as you get further out of it for reasons we talked about in the last lecture. And then it's still a metal sphere out here. And then out here, when you're finally outside of all of them, there's still an electric field, so long as that there's some sort of net charge, right? Because Gauss's law, this dashed line is really our Gaussian surface. And so if that Gaussian surface encloses any charge, any net charge enclosed, that's going to give an electric field. So for example, if I tune this thing to, instead of being 4Q to 2Q, we should find that there is no electric field outside this thing. Because again, the charge enclosed would be 0, so I'm going to do that. On the worksheet, I asked you guys questions like, what's the strongest electric field? Is it inside or outside? These are all fair questions for the exam. The exam will have a Gauss's law question on it. Yeah, so you notice that once we're out here, there is no electric field out here because, again, it's +2 on the shell and -2 on the shell. The other thing to note, I'm going to go ahead and change this back to 4 just for the heck of it. The other thing to note that I think is important is that you can use Gauss's law to, along with the fact that the electric field is 0 inside a conductor, to figure out how much charge is on various surfaces. So this metal shell out here, if you wanted to know how much charge is on this inner surface, is actually telling us. It's telling us that the charge on the inner surface is 2Q, right? Even though the total charge is 4Q. But the way to think about this is that if you draw a Gaussian surface just in the middle of this metal shell, and you do that integral, right, of the integral of EA, well, E is 0 inside of this thing. And so that integral is 0, which means the charge enclosed is 0. The only way the charge enclosed is 0, given the fact that there's -2Q in here, is if there's +2Q on this inner surface. And so Gauss's law can tell you useful things like how much charge is on this inner surface. Now, once you have all the charge on this surface, how do you figure out the charge on this surface? Well, if you know the total charge, which in this case is 4Q, well, then on this edge, it's going to have to be 2Q of charge, so the total adds up to 4Q. So Gauss's law can help you do these types of problems as well. And so not only figuring out the electric fields, but also helping you to figure out what the total charge buildup on various surfaces. Even though in the middle of this thing the electric field is 0, it can still tell us what the charge is on those surfaces. Okay. So the problem I just did, which had a spherical shell around a solid sphere, there's analogs to that in cylindrical geometry. So if you're trying to get into my head about what could possibly be on the exam, well, there's only a couple of geometries where this even works, and so you can do similar calculations and conclude, instead of how much charge is enclosed, it's sort of charge per unit length enclosed, and those sorts of things with the cylindrical geometry. Likewise, with these two sheets, if one of these sheets is positive and the other one's a negative, right? If one's positive and the other one's negative, well, then you can do Gauss's law analysis and say, all right, well, if my Gaussian surface goes all the way through both of them, well, then there's negative charge enclosed here, positive charge enclosed here. If these two surfaces have the same total charge, then the charge enclosed in our Gaussian surface is 0. If the charge enclosed is 0, that tells us that probably the electric field is 0. And so part of the reason why the electric field cancels out here if you have a positive and negative sheet here is that the Gaussian surface analysis, the Gauss's law analysis, tells you that that would be true. So, a more general way of writing this equation would be like this. So this, if it is the negative of that, you end up with 0. Okay. So that's about all I had for today. I hope that was useful. And see you guys in class.